This is the squeeze theorem. It states that suppose x is equal to the x sub n sequence, y is equal to y sub n sequence, and z is equal to z sub n sequence be sequences of real numbers with y sub n be greater than or equal to x sub n but less than or equal to z sub n for all natural numbers n, and that the limit of x sub n is equal to the limit of z sub n, then y, which is equal to y sub n or sequence y sub n, is convergent, and that the limit of the three are equal to one another. You have the limit of x sub n sequence is equal to the limit of y sub n sequence, and it's equal to the limit of z sub n sequence. This is called the squeeze theorem because it tells us that if there are three different sequences of real numbers where we can structure this order for all natural numbers n, but the limit of x sub n and z sub n are actually equal to one another, this tells us that the limit of the middle sequence, in this case y sub n, is equal to the 2, and thus the y sub n is convergent to that said limit. So we need to structure this proof in this manner. Okay, so we are going to start by letting, or suppose, of course, assume the assumption. Suppose x is equal to x sub n sequence, y is equal to y sub n sequence, and z be equal to z sub n sequence be sequences of real numbers. So we'll have this assumption here, very important, with this inequality: y sub n is greater than or equal to x sub n but less than or equal to z sub n for all natural numbers n. Okay, so we have assumed this, and of course, very important also, the limit of your x sub n is equal to the limit of your z sub n sequence. Okay, so we are done with our assumptions, and take note, we are talking about limits of sequences specifically. So per definition, we may not be using, or we will not be proving limits here, but for a definition of limits of sequence, we need to structure this in this form, the general form, where x sub n is a sequence. This is its limit. The absolute value of their difference is less than epsilon. Again, we may not be proving limits here, but we are going to show this because part of our target is to show that the limit of the sequence y sub n is equal to the limit of this, and whatever will be the representation of them, we will be going to touch this definition itself. And with that, of course, we're going to introduce epsilon again. Okay, so let's start with our proof here. So we're going to have let epsilon be greater than 0, so that epsilon will come out later on. And of course, okay, a representation for this equality, you will have here w be the equal to the limit of x sub n sequence, and also equal to the limit of z sub n sequence. Okay, so we're doing this representation so that we could return to this per definition, because if epsilon is greater than 0 and the limit of x sub n and z sub n is equal to w, then it follows that x and z converges, definitely it converges to w, because w is the representation of the limit of their sequences. In that, let me change the color of my pen to black, and that there exists, because this is per definition, k, which is a natural number, okay, such that, and here comes the part of the definition, so that we can invoke this, okay, and such that if n is greater than or equal to k, then per definition now, we can structure it in this form. Take note, the limit of the x sub n sequence is w, so you will have here x sub n minus w is less than epsilon per definition, and this is also true for the limit of z sub n, so the absolute value of z sub n minus w is also less than epsilon. Again, these are all per definition. We are not going to prove the limit per definition, but we are going to use this as we look into the goal. The goal is to show that the limit of y sub n is equal to the 2. So we are going to also touch this portion, and that is also the additional point that it also converges. Okay, so before we go to the involvement of our y sub n, we have these two forms now, and one of the definitions or properties in absolute value notation, let me write here in other form. Okay, so you will have here, say for example, absolute value of A is less than B. We have a theorem, or part of the theorem or definition, if of course if B is greater than 0, this one here, then we can structure this absolute value notation as A, whatever will be inside is greater than or equal to the negative of B, but less than or equal to B. This is again one of the corollaries or theorems, I think, properties of absolute value. So since E, or not E, epsilon, already described earlier as greater than 0, so this meets this criteria. Hence, for both of them, okay, this implies that both of them, both of these two, can be structured in this form here. So we start by x sub n minus w. Okay, we're taking the inside of the absolute value notation greater than the negative of epsilon but less than epsilon, and for this structure here, you will have also z sub n minus w is greater than negative epsilon but less than epsilon, using this definition. Okay, so let's take a look at this and make this as asterisk. We're going to return that later. Okay, we're going to look into the other assumption, specifically this inequality here. So we are going to write it here. Y sub n is greater than or equal to x sub n but less than or equal to z sub n for all n natural numbers. This is part of our assumption as well. Then if we subtract, okay, if we subtract this by w, okay, which is the limit that we have described earlier, this is also true to be subtracted from all of this, okay, and this here as well. Take note, this is one of the properties of inequality. Once you add or subtract something here, do the same thing for all. It will not change the inequality. Okay, so with that, this is our double asterisk. Okay, so hopefully this is clear now. Now, why is it that we are talking about this? Because by your asterisk earlier, this one here, which corresponds to these two, take note that the x sub n minus w, which is also here, this is, I'm taking this part only here, okay, that is greater than epsilon. And take note that z sub n minus w, which is this one here, taking this portion, is less than epsilon. So that would mean you will have y sub n minus w is greater than or equal to x sub n minus w, which is this one here, still greater than negative epsilon. On the other side, this is less than or equal to z sub n minus w, which is this, but taking this portion here, which is still less than epsilon. Okay, this gives, as we remove this portion and this portion here, we will have y sub n minus w is greater than, because this is only greater than negative epsilon but less than epsilon as well. Okay, I don't have much space. Let me copy this entire form here. Pardon for that. I'm going to use another space here, page rather, in pasting this. Okay, so once we reach this portion here, okay, looking into that and going back to the previous page, as this form, let me remove this and that, all of the scribbles here, because this form is just equal to that, and this form is equivalent to this. Take note, this is the structure minus epsilon greater than greater than minus epsilon and but less than positive epsilon. So looking into the next page, the same structure here. So per definition of this structure, absolute value, this one here, hopefully you can see this scribble, then we can return to this form. Okay, taking the middle term as inside absolute value notation, and this b be equal to that. Okay, so taking this, you will have here, which gives us the absolute value of y sub n minus w is less than epsilon. And what is this, by the way? Okay, this is the definition of the limit of the sequence. Going back here, pardon again, this here, once we constructure this form that the absolute value of a sequence and a value is less than epsilon, then this is the limit of this sequence. In short, this is the limit of this sequence. So we'll have here, hence, we will have the final statement in proving limits. Since e greater than 0 is arbitrary, this is what we have been doing before in proving limits. This implies that our y, which is equal to the sequence y sub n sequence, converges to w, okay? That is the limit of y sub n is equal to w. Okay? Further, this is now what we are trying to show. Now that we have shown that this is w and these two are already w as declared here, as assumed here earlier. Okay? Further, the limit of x sub n, this is w, right, is equal to the limit of y sub n is equal to the limit of z sub n. Okay? Or we can simply remove this to achieve what we are trying to prove. So we have shown that with all of these criteria, y converges w and the limit of the three different sequences are equal to one another using these methods, these processes, which is the goal of this squeeze theorem. Let me remove all the scribbles here for you to see the final form of the sequence, the theorem, and this we have proven already. So please review this video for understanding the squeeze theorem and probably all of its implications soon. Thank you very much for watching.